All right. Joshua.
Here.
Emily. Here. Willow. Ava.
Here.
Michael. Luke. Alexis. Here. Jamie.
Here.
Adelaide.
Here.
Justin.
Here.
Brooks.
Here.
Kaylee.
Here.
Ashlyn.
Here.
Spencer.
Yeah.
Chronicle.
Here.
Chloe.
Here.
McKenna. Carter. Kevin. Allison.
Here.
Tal.
Here.
Cooper.
What's the orange cat's name from Garfield?
Garfield.
Oh.
Cooper.
Yes. No.
Tucker.
Here.
Conley. Riley.
Here.
All right, came in late. Be sure you sign in as late. All right, I'll give you just a second to get logged in for your attendance. And then go ahead and work on your bell ringer, and then I'll explain a couple of things. All right, so on your Google Classroom in the stream, the first thing I put, this is your test. I went over it as if I was taking it. Teachers have to do a video for tomorrow for the V-Day, and I just thought, well, I was gonna do that for them, so I'll just let everybody see it. So I'll let you watch that. It's very short, 7 minutes. But just walking everybody through that. Second, right here, if you scored less than a 7 out of 10 or 70% on the test, I have scheduled you for flex. If you're not in there yet, you will be. It takes a little bit of time. There's no flex tomorrow, so I couldn't pull anybody in tomorrow. So the earliest I could pull people was Thursday. So I'm trying to get it done between Thursday and next Tuesday, just because we don't want to run into the next test. So I put, if you have to remediate, you'll have this on your Google Classroom. So it only got posted to people that got less than 7 out of 10. And all it is it's just a very quick extra practice remediation on Lewis structures. Okay. You have to have that done before I can let you retest. If it's not done, when you come in for remediation, I'm going to make you do that first, and then I'll let you retest. Okay. So Like I said, it's only going to show up on your page if you got less than 7 out of 10. All right, is that clear of mud? All right, so the video is me taking the test as if I'm a student. And then information about the criteria for retaking the test. As soon as I posted that to the stream, I had 4 people, can I take the test? Did they even read what I put? Okay, so always read that. All right, so today we are going to do a bell ringer. A little bit of fun. You don't have to name any all of this at least, right? So you've got your Wurtzer periodic table. So you're going to be using the element symbols to figure out what the words are. And they give you a hint. This one's easy. Take a couple of minutes. This one we don't have to worry about in the US. You go to India, you do, but so take a minute, do that. Put your phone up, sir.
Anybody got a charger? Hey, can I have a charger? No? No? Oh. 70.
It doesn't really make sense. Is this supposed to make it work?
You have to unscramble them.
Oh, I didn't. Makes sense.
You gotta unscramble them. All right. So if you unscramble these two, what do you get? Race. You don't want to be last in the race. You want to be first. All right, a masked bandit. This is my son's spirit animal. He has 30 stuffed these.
Raccoon?
Yes, raccoon. Some of them have been packed up into boxes, and I'm going to dig every single one of them out when he has a senior pictures taken. All right.
That's cool.
If you're not anybody, you must be nobody. Okay? And then beware of this snake. Yep. Like I said, we don't worry about that in the United States because they are not indigenous. All right. So in your Google Classroom, you have all right. All right, so you have a short article to read on atomic radii. The second half of your first test is on periodic table trends, atomic radius, ionization, metallic versus non-metallic characteristics. And so that test, I think I have it scheduled not for next week, but the week after. But I was just going to kind of see how it went because it's not that big. It's pretty short, but the main thing is being able to get the lab in on Wednesday. We were going to do it today, but I'm short a couple of pairs of pliers. So I got to go to the store and get some pliers. But anyway, yeah, you guys are sitting there thinking, why do we need pliers for a chemistry lab? We do. It's one of those things. All right, so I'm going to give you 10 minutes and have you read. And then we're going to go over it. And then you'll have some questions. And I've a short video to show you that kind of sums everything up about the trends. And then if you have the remediation to do, you'll have time to do that. Okay, so 10 minutes. And because this is in a Google Doc, you can highlight and annotate as you need to. some of you still haven't signed in for attendance either. Did you read it? Give me just a second. We're getting ready to go over it. Okay, doctor. All right. First of all, in today's day and time, this is bad. Kind of looks like Sturgis. You guys know what I'm talking about. You may not.
Yeah. So
All right. So luckily, this is an old picture. This isn't something that has happened since COVID. But my first thought was it looked like Sturgis. So anyway, all right. So how come all these people can fit in such a big spot or a small spot? Yeah. So when you have events, it tends to draw large numbers of people. Okay. So even an outdoor event can fill up, so there's no room for more people. And that's one of the things is a lot of people make fun of me because I don't like concerts. They're like, oh, we went to see so-and-so. And I'm like, oh, how was it? Oh, it was great. You didn't go? And I'm like, I don't like crowds. This COVID thing has actually been good for me because I can't stand to have people stand like next to me. So I'm enjoying that 6-foot bubble of people that I don't know. Now it's different if I know the person or the people, like if it's a student, not a problem because I know you, okay? And I know at some point during the school week you belong to me for a little bit and I'm okay with that. But this would be completely unnerving for me. I couldn't do it. Could not. That when you get into big crowds like that, people tend to act like stupid heads. So, All right. Crowd capacity depends on the amount of space in the venue, and the amount of space depends on the size of the objects. Obviously, you would not be able to get that many elephants in that space, right? Well, maybe if you shrunk them, I don't know, Shrink-A-Ray, Mr. Drew's Shrink-A-Ray. Okay, never mind.
Oil.
All right, atomic radius. The size of atoms is important when trying to explain the behavior of atoms or compounds. One of the ways we express the size of an atom is with its atomic radius. So we have talked about a model of the atom. We talked about Bohr models, and I said after the test, you won't have to draw them again. Unless you're remediating, then you gotta draw them again, okay? But the size of those orbitals can change. Because electrons have a negative charge. And what do we know about like charges? Do they attract or repel? Think of magnets. Think of magnets. Like charges repel. Electrons are negatively charged. Are they going to want to be stuck next to each other? They don't want to look like that picture up there. Okay? So the more electrons there are, the more they're trying to spread out away from each other. And because of that, the radius of an atom gets bigger and bigger. Now, it's not this big. Okay? They are so tiny. I couldn't even tell you how many atoms could fit in this space. Okay? But this helps us understand why some molecules fit together and why others don't. The size of an atom is defined by the edge of its orbital. Okay? Those shells that go around the nucleus are also called orbitals. The more electrons there are, the more that orbital is going to swell. It wants to spread out. Those electrons don't like each other. They want to get away from each other. All right. So in order to standardize the measurement of atomic radii, the distance between the nuclei of two identical atoms bonded together is measured. Now, you probably recognize this. Seen that before? Yeah, that's the area of the circle, right? Well, sometimes they don't tell you what the radius is, do they? But they give you the diameter. And the way you figure out what the radius is you take the diameter and you divide it in half. Voila. Okay? And you thought that that geometric formula was not useful outside math class. But here it is. Lo and behold, you're using it in science. All right. All right, atomic radii have been measured for elements. The units for atomic radii are picometers. All right, let me see if I can remember how to write this. That's 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. That's how small a picometer is. Okay? That's a 1 with 11 zeros in front of it. Teeny. All right? As an example, the internuclear distance between two hydrogen atoms and an H2 molecule is measured to be 74 picometers. Tiny. Teeny tiny. Okay? All right. I love this diagram. I really do, because you can think about the trend of the periodic table, but to actually get a picture, an illustration of what in the heck they're talking about makes things all better. Okay? So as you move from right to left, so you're going backwards across the periodic table across the top, the radius of the atom's getting bigger. Okay, those nuclear forces are having less and less effect on the electrons. The electrons are trying to break away. And we have talked about what happens in these two columns with the electrons. We've talked about how they like to fly away. That makes sense. They fly away because their atomic radius is so big, they can break away. They can be free. Those protons can't hold them in. So they break away, they fly away. Whereas we know on this side, except for that 8th group, we know that this side right here, they crave electrons. Okay? So they're going to go, I'll take them. And they're tightly knit and they're happy. Then as we move from the top to the bottom, again, we start to see that radius is getting bigger and bigger and bigger, because there are more and more electrons that are trying to break away. Okay, so the radius of the atom is getting bigger as we move from the right side to the left side, from the top to the bottom. So the biggest one, or the smallest one, this is the smallest. And this guy over here, that's the biggest. Okay. Now I have on Wednesday, if it's back on the printer, when I ran these off this morning, you can't really read them very well. So send them to the print shop because they'll have a better picture quality. But this is going to have all the trends on it, and you'll be able to attach it to the back of your periodic table. So on your next test, you'll be able to look at it and go, oh yeah, atomic radius this way, ionization that way, etc. It'll be on your test, and it'll be on your periodic table, which will be nice. Any questions about this right here? Okay. This is yet another thing I did not learn in chemistry. And I can't even be too upset about it because my chemistry teacher's dead. So, you know, he died the year after I finished high school. So, yeah, I know, right? He smoked like a chimney. His classroom was right next to the boiler room, and you could smell it. And I had his class right after lunch, and he'd come in, and oh my goodness, it was bad. All right. The atomic radius of atoms generally decreases from left to right. There are some small exceptions, as always. But within a period, so the row, within a period, protons are added to the nucleus as the electrons are being added in the same principal energy level. So remember, the word period equals row. These electrons are gradually pulled closer and closer to the nucleus because of its increased positive charge. So they're hugging them, they're hanging on to them. They're like, no, you're not going anywhere. You're going to stay with us. Since the force of attraction between nuclei and electrons increases, the size of the atom decreases. Holding it tight, bringing it together, saying, hey, electron, you belong to us. And hang on to you. The effect lessens as one moves further to the right because of the electron repulsions. They have the same charge. They want to get away from each other. Otherwise, you'd have a really, really big atom. And what do we know about atoms that get too big? What happens? They don't get destroyed. You can't destroy them. We use it to our advantage. What do we do with this guy? 1945, Japan. Okay, we took advantage of the nucleus of the atom being too big. So we struck it with another atom, knocked into it to make it split. Okay, so that's the reason why atoms can get big, but under certain circumstances, you don't want them to get too big. You don't want to, it's like blowing up a balloon. What happens if you put too much air in a balloon? Pops. Okay, in 1945, it caused some issues. All right. The atomic radius of an atom generally increases from top to bottom within a group. So remember, group equals column. Okay. Like I said, I put this in the Google Docs so you could highlight and make notes. As the atomic number increases, down a group, there's again an increase in positive nuclear charge. However, there's also an increase in the number of occupied energy levels. As we learned in our Bohr models, as we go down a level, we're adding another shell up to 7, right? So that makes sense. Higher principal energy levels consist of orbitals which are larger in size than the orbitals from lower energy levels. The effect of greater number of principal energy levels outweighs the increase of the nuclear charge, so the atomic radius is getting bigger. More stuff in the atom. Electrons are freer to move around. That's a good thing, okay? Right here, the electrons moving around. We want that. We like electricity. And then what the other thing that I love about this is it kind of gives you a visual, just to kind of help you understand, hey, as the atomic numbers are doing this, this is what's happening to the size of the atom. How big is that nucleus getting? How big are those orbitals getting? All right, short video. And it's actually more of a slideshow /
Atomic radius. Atomic radius is the average distance between a nucleus and the outermost electrons. Usually this is measured as 1/2 the distance between two nuclei of an element in its elemental form. So two of the same elements, if I were to draw this element, I'm just going to put a dot for the nucleus, but imagine there are protons and neutrons in there. And then I'm going to draw another element, the same element, and then I'm going to draw this line between them. Okay, so this line between them. And what the atomic radius measures is actually half that distance. So because they're radii and they have the same length, these two things should be the exact same. So radii means that anywhere, if I pointed out that radii from anywhere, it would be the same distance. So that's what atomic radius is.
Hold on.
Atomic radius is the average distance between the same length. These two things should be the exact same. So radii means that anywhere, if I pointed out that radii from anywhere, it would be the same distance. So that's what atomic radius is. We can use the periodic table to notice trends that happen to different elements and their atomic radii. So periodic trends for atomic radius is atomic radii decrease from left to right across a period in the periodic table. So as I go from left to right in this direction, I decrease my atomic radius. And that makes sense because as I get more and more protons, I have more attractive force for the electrons that are in the same energy level in that period, so I can draw them closer to me. So it is very easy to see that protons, when you have more protons, keep adding protons when you move from left to right, you are decreasing the distance because you're pulling them closer. Atomic radii increase, though, from top to bottom. So as you go from top to bottom, it increases because now you're adding more energy levels and more orbitals. So as you move up energy levels, the atomic radius gets further away because even though you have more protons, it's not necessarily enough to attract them closer to you because you are moving up energy levels. So here's another way to look at it on the periodic table. As I move from left to right, I am decreasing because I decrease the atomic radius size, so I'm getting smaller and smaller. These things are getting smaller and smaller. because I have more protons at that same energy level. So C has a smaller atomic radius than B and has one smaller than C, and so on and so on. As I go down, though, I increase. So as I go down, these elements get bigger and bigger and bigger. The distance between the nucleus and the outermost electron increases. So Na has a bigger atomic radius than Li, K has a bigger atomic radius than Na, and so on and so forth.
In 1869, Dmitry Mendeleev published the precursor to our modern periodic table of elements. In Mendeleev's table, the elements are arranged by increasing atomic weights and grouped according to similar properties. Mendeleev had to leave blank spaces in his periodic table in order to group elements by their similar properties. He quickly realized that these blank spaces corresponded to then undiscovered elements. Using his periodic table, Mendeleev predicted the properties of 8 unknown elements. These elements were indeed later discovered. The arrangement of elements in the table by increasing atomic weight shows a pattern in which properties of the elements are repeated. The modern periodic table now arranges elements based on increasing atomic number. However, Mendeleev's original premise still holds true. The periodic law holds that properties of elements repeat with increasing atomic number, as the table shows. We can use this periodic law and the way it is represented in the layout of the table to understand chemical, physical, and atomic properties of the elements. Moving from left to right on the periodic table, the atomic radius of the elements decreases. Ionization energy increases. Electron affinity decreases. And electronegativity increases. Moving from top to bottom, atomic radius increases, ionization energy decreases, electron affinity generally increases, and electronegativity decreases.
And you're gonna get this exact picture. It won't be in color, but you're gonna get it.
These properties can be related to the nonmetallic and metallic characteristics of the elements in the table. The columns of elements on a periodic table define elemental groups. Elements contained within a group share common properties. The similarity of properties is partly because each group of elements has the same number of valence electrons. Moving from left to right, the number of valence electrons increases. Elements in group 1A, such as lithium, have 1 electron in their outer shell. Elements in group 2A, including magnesium, have 2. Elements in group 3A have 3. Elements in group 4A have 4. Elements in group 5A have 5, and so on. Using this information and the octet rule, we can predict how an element will behave when it forms bonds. The octet rule states that elements will gain or lose electrons to achieve a noble gas valence of 8 electrons. Elements will react so that they lose or gain the fewest number of electrons to have a noble gas configuration, requiring the least energy. We can therefore use the periodic table to predict whether an element will gain or lose electrons when it forms bonds. Let's make a prediction for the element oxygen. Oxygen is in group 6A on the periodic table, so we know it has 6 electrons in its outer shell. To have a complete outer shell of electrons, an atom of oxygen needs to gain 2 or lose 6. Gaining 2 electrons takes less energy than losing 6. Therefore, oxygen will gain 2 electrons when forming bonds. Because carbon is in group 4A, we know it has 4 valence electrons. To follow the octet rule, it would have to gain 4 or lose 4 electrons. Because this loss or gain would take the same amount of energy, carbon can gain or lose electrons depending on the other elements it is combining with. Sodium, which is in group 1, has 1 electron in its outermost shell. The least energetic path is for a sodium atom to lose 1 electron. Chlorine, which is in group 7A, has 7 electrons in its outermost shell. The least energetic path to a noble gas configuration is for a chlorine atom to gain 1 electron. When the 2 elements react, sodium loses an electron, Chlorine gains 1 electron. Sodium donates its electron to chlorine. The reaction creates a molecule of sodium chloride, which you know as table salt. Mendeleev's arrangement of the periodic table over a century ago allows us to understand an element's chemical, physical, and atomic properties simply by looking at its position on the periodic table.
All right, so what you have left to do is I put this on here for you. This one's nicely brightly colored, just for reference, but showing you the direction of atomic radius. And notice how it's color coded. So here's ionization, electronegativity, electron infinity, metallic characteristics, non-metallic characteristics. So that's just kind of a reference sheet until ours gets here from the copier. Like I said, I tried to copy it this morning, but the toner was low, and it's really, I mean, I could read it kind of. So these will be backups in case you lose the periodic table, which I hope you will not. All right. So what you have left to do, you have this Google right here to do. I see 3 of you have done it. And then if you are remediating, the Lewis dot practice is right here. If you're not remediating, it won't be there. Okay? Now, I may have missed a couple of people. I'll be double checking tomorrow since I'll be sitting here in my room by myself. And I'm going to let you work, and I'll check in with you in 20 minutes.